Hey everyone, welcome to this explainer. Today we're diving into a really fascinating and honestly, absolutely critical topic. We're calling it AI Needs Its VMware Moment, Sustainable AI Infrastructure. Let's get right into it. Okay, let's dive into this massive paradox sitting right at the heart of the AI boom. The sheer physical infrastructure required to support all this new intelligence, it is growing at a staggering, deeply resource-hungry rate. Now, it's really easy to see sleek sci-fi concepts like high-tech data centers nestled right up against natural environments and think, wow, the future is all about floating servers or giant ocean pipelines. But I'm going to let you in on a little secret right off the bat. The most sustainable AI facility on the planet might actually just be the one that doesn't need all that extreme cooling, simply because it uses its existing infrastructure more intelligently. Which leads us to a really uncomfortable question, one we desperately need to ask ourselves. Are we currently building the most intelligent systems in human history using a distinctly pre-virtualization infrastructure mindset? I mean, really think about that for a second. With all the extreme density, the massive power draws, and these huge liquid cooling systems we're pouring into modern AI factories, are we just blindly assuming that bigger is automatically better? If you remember enterprise IT before the era of VMware and virtualization, you know we used to solve growth with a very brute force formula. More applications literally just meant buying more physical servers. We built larger server rooms, we bolted in more racks, and we ran single workloads on machines that sat practically empty, just underutilized for most of their lives. Virtualization completely changed the game by pooling all those resources together. But right now, we are making the exact same historical mistake with AI. We're just trading that old-school physical server sprawl for a much, much more expensive phenomenon, GPU sprawl. Let's look at the symptoms. You're probably going to recognize a few of these bad habits. We're seeing dedicated clusters set up for single, specific models. We see business units hoarding capacity just in case, treating it like a security blanket. We've got high-end, wildly expensive GPUs being totally wasted on basic workloads. Or worse, sitting completely idle while jobs wait on human approvals or data preparation. We even see the largest available models being selected by default, without anyone stopping to check if a smaller model could produce the exact same result. Capacity quickly becomes this protected organizational territory instead of a shared enterprise resource. And while these might seem like minor operational hiccups, at AI scale, every single wasted GPU hour piles up into a massive, wildly expensive draw on power and cooling. And speaking of cooling, this is where we inevitably slam into the physical reality of what this sprawl is actually costing the planet. The big, hidden resource crisis everyone is asking about right now is, how much water do AI data centers actually use? This is a huge public concern. Specifically, this whole debate centers around evaporative cooling systems. This is where water carries the heat away from the servers, evaporates into the atmosphere, and then requires a constant flow of fresh makeup water just to keep the facility running safely. Now, to be fair, evaporative cooling is a proven, highly conventional thermal management model. It's not an engineering failure by any means. But here's the catch. Because these AI campuses are scaling toward hundreds of megawatts and soon gigawatt-class ambitions, that massive scale means we can no longer treat water availability as just some secondary facilities detail. Water availability has to become a first-order architecture constraint. We literally can't just ask if a site can structurally support another cooling tower anymore. We have to escalate the conversation. We need to ask a much deeper, far more challenging question. At what point does a supposedly efficient data center become an inefficient use of the community around it? Responsible infrastructure leaders absolutely must look at regional watersheds, local water stress, and the broader community impact well before a single drop of concrete is poured or a single massive GPU cluster is ever ordered. It's not just engineering anymore, it's a critical community responsibility. Now, here's where we pull the rug out. This is the big turning point. Every wasted GPU hour isn't primarily a cooling problem at all. Actually, scratch that. It's not a cooling problem. It is fundamentally a utilization, orchestration, and governance problem. We are wasting incredibly expensive hardware, which in turn continuously and needlessly wastes the water and the power. So how do we actually fix this? Well, we need to build what we could call the VMware of AI. Now, this isn't going to be a single magic product. It's a whole stack of capabilities. Let's break this down layer by layer. First, at the hardware layer, we need GPU partitioning, meaning virtually slicing up these massive accelerators so small jobs don't hog a whole GPU. Second, the orchestration layer. We need intelligent scheduling that actually understands network topology and data gravity, not just whether a chip happens to be technically free. Third, we have the control plane layer, which brings back those solid enterprise policies like quotas, queuing, and chargebacks. And finally, the model layer, using precision selection and request batching. Basically, continuously asking if a workload actually needs the massive infrastructure it's asking for in the first place.
So, the crucial point here is that things like fractional allocation, GPU pooling, and intelligent scheduling, they aren't just clever operational or financial tools. We need to treat the platform layer as a sustainability layer. By making accelerated compute truly shareable, schedulable, and accountable, you drastically reduce the physical footprint required. These software and platform efficiencies are literally conservation technologies.
Of course, high-density AI is still going to require fundamentally better thermal engineering, and the industry is exploring some truly fascinating, almost sci-fi frontier ideas. I mean, we're seeing concepts ranging from direct-to-chip liquid cooling to Google's Hamina data center in Finland, which successfully uses coastal heat rejection directly from the sea. Then there's Nautilus data technologies using natural water loops, Microsoft's Project Natick testing actual underwater server deployments, and even thought experiments about putting data centers into orbit. These are super exciting because they challenge the old assumption that we have to forever rely on freshwater evaporation.
But let's ground those frontier ideas in reality for a second. Build it near the ocean is simply not a complete strategy. While coastal or natural water heat rejection brilliantly keeps the seawater separated from the facility's clean cooling loop, it still comes with massive engineering challenges. You have to carefully solve for corrosion, biofouling, thermal discharge, and the real impact on the local marine ecosystem. The goal here isn't to just shift an environmental problem from our municipal water systems directly into the ocean. It has to be engineered responsibly. And here's the kicker. Even if we perfect our cooling and we perfectly virtualize all our GPUs, we run straight into a fascinating and somewhat uncomfortable academic concept, the Jevons paradox. This paradox states that when a technology becomes cheaper or more efficient, demand can increase so much that total consumption actually rises rather than falls. This is the efficiency trap. Virtualization taught us this exact lesson before. We solved physical server sprawl only to instantly create VM sprawl. If we make AI inference incredibly cheap and hyper-efficient, organizations might just turn around and deploy thousands of new automated workflows and agentic activities, rapidly eating up every bit of the resources we just saved. Which brings us to a really hard truth that we just have to internalize. Efficiency alone is not sustainability. Yes, obviously, smarter infrastructure is absolutely necessary, but it will not automatically shrink the aggregate AI footprint without strict governance, transparent measurement, and highly intentional choices about where and when demand should actually be allowed to grow. And this brilliantly illustrates the next step. How do we actually govern this? We need a fundamentally better AI infrastructure scorecard. We have to move way beyond simple PUE or power usage effectiveness scores. We need to start measuring resource yield. Think along the lines of liters of water per million quality-adjusted tokens. We need hardware yield, meticulously tracking GPU utilization by workload type. We need policy impact, measuring queue time versus actual runtime, and ultimately business impact. How much water and power are we actually spending per useful business outcome? It fundamentally shifts the entire perspective. A data center shouldn't just be judged by how much raw compute it holds, but by how intelligently it converts constrained natural resources into real, valuable outcomes. Which leaves us with this final, truly powerful question. How do we produce more useful intelligence while demanding less from the world around us? Thank you so much for joining me for this explainer. I really hope this structured look at the data leaves you viewing AI infrastructure in a whole new, much more focused light.